Dear guests, it is a privilege to have with us today Professor Leslie Valiant, and he will present a plenary topic entitled Where Neuroscience Meets Computer Science. Professor Valiant is currently the T. Jefferson Coolidge Professor of Computer Science and Applied Mathematics at the School of Engineering and Applied Sciences at Harvard University. His research has spanned multiple areas, ranging from theoretical computer science to parallel computation, as well as artificial intelligence and computational neuroscience, among others. He's also an author of 2 books, Circuits of the Mind and Probably Approximately Correct. He's a recipient of the Neven-Lena Prize of the International Congress of Mathematicians, as well as the 2010 AM Turing Award. He's a fellow of the Royal Society and a member of the US National Academy of Sciences. Let's welcome Professor Valiant.
Thank you very much for the very kind introduction. And thank you to the organizers for inviting me. And thank you, the audience, very much for coming. Science comes in many varieties. So some projects are short, and you can complete it in a month. Some take a year, some take much longer. So the one I'm going to describe, I've been doing for more than 30 years. And it's not quite finished. So it's very much an ongoing project. Some science projects are in one specialized area, and most of them are, and there are good reasons for that. And some projects try to bridge different areas. So the one I'm describing obviously tries to bridge 2 areas. And so in my experience, this is quite difficult because although people describe how specialists in different areas can come together and do productive work, in my experience, it's usually the single scientist who has to try to understand more than one area, and that can meet with difficulties. So what this talk is about how computer science may be able to help us understand how the brain works. So neuroscience has a very rich set of experimental techniques for finding out about the biology of our brain. But to describe at a high level what functions the brain is doing, the right language for that is computer science. So this is an ideal opportunity for these 2 fields to interact. So the point about the brain is that while a vast number of things are known about it, it's amazing how little we know. So a very basic question of how many neurons we need or we use to store a memory of, say, one event, or maybe one person. So if at GYSS you meet a new person and you remember the person for a while, how many neurons do you devote to this task? Is it 1? Is it 10? Is it 100? Well, we have about 10 to the 11 neurons, so maybe it's as large as 10 to the 8. So it's unlikely that the answer is 1 or 10. But otherwise, we really, just do not know. And this is astonishing level of ignorance on such a very basic question. And the question is, why is this so difficult? And so the approach I'll take from computer science, the methodology is the following, is that if you take an easy problem, like storing some information for a computer is very easy. And if you name such a problem, then maybe there are so many different ways of implementing it that it's hard to discover which one the brain has chosen. And that seems to be the case, that we haven't been able to discover how the brain does this. So this methodology is to invert this. And the idea is that if there are fewer ways of implementing something, if it's something hard to compute, then perhaps this gives us a clue. It narrows down the possible solutions the brain might be using to implement this. Okay, so this is the idea. And just to illustrate this, so this is an illustration of some interaction between a cognitive task and computational difficulty. So this task is, for the light bulb problem, it's an imaginary task. So there's a large number of light bulbs, maybe 1,000 in front of you, and they're each flashing on and off with a period of a second. So if you look at one light bulb, it's either on, it may be on again next second, then off. So each one is randomly on and off with a period of 1 second. And the setup is that each of these 1,000 light bulbs flashes independently, except 2 of them are correlated. So 2 of them will be the same 3/4 of the time, say, and not half the time. Okay. Now, of course, if you just stare at one light bulb, you will just see the sequence of zeros and ones, whether it's off or on. And if you stare at another light bulb, you see that's zeros and ones. And so if you compare these 2 particular sequences, then after a while, you'll figure out whether do they agree about half the time, or do they agree about 3/4 of the time. Okay, but the question is, how difficult is it to tell which pair is correlated? So could you do this for a large number of light bulbs? And so just to put this down, so you've got a large number of light bulbs, each randomly flashing off and on, and they're all independently flashing, except for one pair, which you don't know which pair, and that's correlated. And your job is to find the pair. And the obvious algorithm for doing this would be that you have to focus on each pair. You focus on a pair, you stare at it for a while, look at the zeros and ones, and see whether they agree half the time or 3/4 of the time on the average. But then you've got about n² pairs of light bulbs to stare at, and that takes a long time. Because if you think about it for not very long, in fact, the time you have to observe one pair of light bulbs to see whether they're correlated is just the logarithm of the number of light bulbs. And if you have about some constant times the logarithm of number of light bulbs, zeros and ones, and you observe each light bulb for that long, then that will have enough information in to determine which pair is correlated. So what I'm saying is that for each light bulb, you write down a sequence of zeros and ones of about log n bits, and then you go away and do your computation, compare each pair. But the point is that the obvious method is n². In principle, the amount of information you have is much smaller. So the question is there a fast way of doing this? Faster than n²? And the answer is that people have thought about this for a long time. There are various algorithms, and the best algorithms are better than n². You can get them like n to the 1.6, but they're very complicated. Okay, and certainly there's no easy way of doing this, as far as we know. So this looks like a problem with some inherent computational difficulty to the best of our knowledge. So the question is, what does this mean as far as cognition? Well, I think what it means is that I'd be amazed if a human could do this problem on a large scale. Because, of course, it's hard to exclude. It's possible that the brain is especially wired to do this problem, but it's unlikely. But so it looks like, so without carrying on about this anymore, so I think this is a problem with some inherent computational difficulty. And for that reason, we are bad at it. Okay, so given 1,000 light bulbs, I don't think anyone could solve this problem very well, except by staring at each pair of light bulbs in turn, and that'll take a long time. Okay, so this is a problem which I think is too difficult, we cannot do. So this is not interesting. So what problems are interesting to help us find out how the brain works? And so I'll look at symbolic processing. What symbolic processing is that we can tell each other lots of stories about discrete facts, and the other person can just soak it up. Okay, so if I say that there's a restaurant called the Green Fox, and I'll tell you that I went there, it was bad choice. It was recommended by Joe. When I was there, I heard the election results. Then you can soak this up, you can remember some of this, and there isn't any great mystery. But the point is that humans can do this kind of thing on a very large scale. We can do this every day, and we can remember much of what we did the previous day. And there isn't any very good explanation or theory of what happens in our brain to do this. The point being that just one single act of memorizing something is a too easy a problem. But if we observe that the brain does much more, it can do this at scale, then it's a more challenging problem, and we have a better chance of narrowing down how the brain may do it. And here already we've got one feature, which is kind of a standard feature in psychology. The idea is that we don't just memorize things as a long list, but we structure it. So chunking is the idea that sometimes from two concepts like green and fox, we chunk it into a single concept, the green fox restaurant. And if you go to a restaurant often enough, then it becomes a primitive concept for you, just like fox was before. That somehow in our brain, not just like having a telephone directory, there's more structure there because some high-level concepts we need to be able to access fast, just as we access low-level concepts. Okay, so human cortex can do these kind of tasks in hundreds of thousands or more in succession and remember things. And there's no viable theory known, even in principle, of how the brain actually does this. Okay. So now we can actually break down even more on why what the brain does is impressive as far as tasks, and have an even more onerous list of things which we have to explain. So I've got a list of 7 here. So one-shot learning. The idea is that after one exposure, you can memorize things. You don't need thousands of exposures. We can do lifelong learning, that we can execute many of these tasks, maybe 100,000, maybe more. So how many things we can memorize in a lifetime? It's a good thing to try to estimate. Also, when we memorize something, it's not just that we write, it's like recording it somehow on a computer. We're also able usually to respond to it very fast. So we can recognize what we've learned years later and very fast. So what seems to happen is that there's some little subcircuit in your brain which incorporates this new information and can execute very fast. So the memorization is a particularly active kind of thing. And furthermore, these subcircuits, these various things which you've memorized, you can even compose together on the fly. So given a situation, you can compose 2 pieces of information you've learned in the past on the fly. So these subcircuits you've learned must have been learned very well, so you can just run with the information. Okay. Now, if you want a theory of all this, you want it to be quantitatively plausible. So we only have so many neurons, they only have so many connections, and the strength of connection is very important, as I'll mention, how much influence a neuron has on another neuron. Also, there's some basic facts about the brain which you have to be faithful to. And one thing is that the long distance connections in the brain, the axons, are one-way connections. So you have to be faithful to these things if you want the realistic explanation. And then, so the last thing, which is maybe become clearer later on, is that what I really want to do is to break up these tasks, which I haven't described very accurately yet. I've just given examples of this restaurant. And I want some small set of primitive tasks and explain how the brain does those and go from there. Okay, so so in this talk, on the one hand, I'll describe what I want this model of the brain to do. And on the other hand, I'll describe some constraints we know about the brain, the difficulties. And these two sides somehow have to come together and match. So there are some very obvious things to say about the brain. The computers have addressing mechanisms. There's a location 137. The brain, as far as we know, there's nothing like that. So the brain is very slow. Maybe 10 milliseconds is the cycle time. So in 100 steps, although it's got an enormous amount of parallel processing, in 100 steps, it can do amazing things. So the algorithms you need are very different. So each neuron is connected to a very small fraction of the other neuron, so it's sparsely connected. So one simplifying aspect of the brain, not everything is complicated. One simplifying aspect is that long-distance communication is very stylized. There's just one way of doing it, and these are these spikes. So basically, as far as long-distance communication, information is just carried by the time a message arrives. There's nothing in the message except for the time at which it arrives. Okay, and then very important are these quantitative constraints. You've got a fixed number of neurons, a fixed number of connections from each neuron, and then this is important that you also have to take into account how well neurons can talk to each other. So synaptic strength. So synaptic strength of 20, K is 20, means that each synapse is only a 20th of the strength needed to cause the neuron to fire and communicate. So if K is 20, it means you need at least 20 neurons to make one neuron pass on this message. So if K is small, then that's a stronger computer, but the brain pays a higher price for having that. Okay, so as far as what's known about the brain which is relevant, so these are some well-known results from about 20 years ago, which show that there's some things which are known. And so this is what are known as Jennifer Aniston cells, or the Bill Clinton cells. So the idea here is that you've got a patient, a human patient, who's got electrodes in certain parts of their brain, usually for medical reasons, but then the cognitive scientist comes in to do some more experiments. So this patient is looking at a picture on a computer, say this picture, and it's looking at this picture between these two dotted lines. And from one cell, there's a recording. This histogram shows you the strength of firing of a single neuron in the brain of this patient. And once you show this, so time goes on from left to right. Once you show this picture, then this cell fires. And then at this line, the picture is withdrawn. And then after a while, this cell stops firing, okay? And so what's found is that for this particular cell, fired when it saw a picture of Bill Clinton, even a caricature of Bill Clinton, but not when it saw a picture of a different American president or an animal or the Eiffel Tower or some buildings. Okay, so how these experiments are done is that earlier, someone shows this patient various pictures and records from some neurons, and then starts suspecting that one neuron responds to Bill Clinton, and then in a separate session collects together pictures, some of which are of the suspected concept and some related concepts, and can somehow verify that in fact this cell, as far as appearances at least, this cell seemed to respond pretty well to Bill Clinton and not to other concepts which you may think are related. So the relevance of this, so this only works in certain parts of the brain, but the relevance is that if you expect to find a cell to respond to some concept like Bill Clinton, then this will only happen if you've got a very large number of cells which do correspond to Bill Clinton. Because if only 1 in a million cells correspond to Bill Clinton, then you'll never find it. So this suggests that large number of cells, the large numbers of cells which correspond to concepts and to natural concepts, which we think are human concepts, like a person, we can find cells which correspond to them. Okay, so so that's okay. So what's the approach we take if there are no viable theories known to a problem like this. So we have to make up a model neural model which respects what we believe happens, and it'll underestimate the brain. So the fact that it's simple is okay, as long as no one complains that our model is too powerful. So then we think up some challenging tasks, and then we show that these tasks can be executed on our model. And then we show furthermore that, in fact, our model can execute thousands of instances of these tasks. Okay, so these are some called learning and memorization tasks. And so basically, we need a model which no one will complain overestimates what the brain can do. As long as we can demonstrate in theory as an algorithm that this model can do it, we'll have one explanation of how it might be doable. Okay, so I'm still trying to explain these kind of things. And I'll explain this is ongoing work still. And the question is, what are these tasks which I want to do, which represent these more predictable examples I've given? So I'll just give two examples. And one is allocating storage for a new concept. So at one time, for the first time, you heard of the notion of an Omicron variant. Okay, so you were blissfully ignorant up to some moment when you first heard of this. So what happened in your brain? Or more generally, what's the task? So the way I formalize the task is that to say that these two words, let's assume you've heard these two words before, Omicron and variant. If not, then there was another stage of learning. But supposing these two words you learned, and the task of memorizing this concept was to memorize a single concept made out of these two. It's like a chunking. Okay, and in particular, so the definition is that if you've already stored items A and B, which is Omicron and variant, then the task is to allocate neurons, to find some new neurons to this item C, and change the circuits so that in the future, when both Omicron and variant were active, then you were reminded of C, because this new set of neurons were caused to fire. So this is the chunking. You're making an equal citizen of this new concept with your previous primitive concepts. Okay, this chunking. So that's one task. And the second task is association. And this association is that you suppose now that you already know what Omicron variant is, and you know what the word dangerous is, but you have been told that this variant is dangerous. So what happens in your brain? So the formalization is that you've got two concepts A and B. A is Omicron variant now, B is dangerous, and somehow through your training, you'll whenever you hear Omicron variant, you'll be reminded that it's dangerous. Okay, so these are two tasks, and I have two more, but okay. So now the model of computation I try to execute it on, I'll just summarize very quickly. So it's okay. So the main points are that I worry very much about resources. There's so many neurons, so many connections, and these are the strength of the synapses. So you have to keep within realistic limits of what the brain has. So the computation is split up into local updates. So each neuron has its own little algorithm which runs on it, and it's discrete. And what this neuron does depends on just what signals it gets from its neighboring neurons. But there's a description, so the local little distributed algorithm running on it. You have to explain all phenomena in those terms. And you also have to discuss timing, which is important in any computation like this. And basically, the timing assumption is very weak. It basically says that each neuron has like an internal clock, which approximately is the same as that of neighboring neurons. And for a few steps, it can keep track of where the other ones are. a very weak timing mechanism. Okay, so just general comments. So it's known now that there are many kinds of neurons and even synapses. And we interpret this to mean that these different neurons are there for a good reason. They run different little algorithms. So we're not looking for the kind of electronic component model where you go out to buy just one kind of component and have clever ways of composing them to make different functions. Evolution has given us many different neurons to do different things, which are useful because that's the most efficient way. And then the other point is that we also know that the brain is very communication challenged, that there are relatively few connections to what could be, and in some sense, all the neurons are waiting for information. And even if the neurons could do some vast amount of computation at each neuron, it wouldn't help that much. So it's communication challenged rather than computation challenged. So what happens at each neuron, defining that isn't so critical, getting that right, because the communication challenge is the limiting one. Okay, so the various issues here, but let's omit those. So I've told you most of the things you need to set up the problem. So for the association problem, what happens? So you've got one concept, the Omicron variant, another concept, dangerous, and what you need to do is to set up connections so that whenever this is active, this will be active. So here A and C are fixed. From what I've told you, I mean, there are these numbers, number of neurons, number of connections, how many neurons are devoted to concept, and how strong synapse is. And this defines for you the problem. So the problem is that when all of A fires, you want at least K of the connections to each of these neurons to fire. Now, in this model, we assume the graph is like a random graph. And then this becomes a concrete mathematical problem, and you can analyze it. And you can see whether the graph can support this association task. Okay, so somehow I've given you all the information you need. The rest is just working out, and you use basic probability theory. So beta is this Bernoulli distribution. Okay, so you do that. So if you're familiar with neuroscience, there's much discussion in neuroscience about Hebb's rule. So Hebb's rule, so Hebb in the 1940s discussed the fact that if you've got two neurons connected, under what conditions does one? What happens if one excites the other? So in some sense, this is a generalization where instead of single neurons, you have sets of neurons. And we believe that at the systems level, this is how the brain works. So the other operation I mentioned are similar. Okay, so one can do computer simulations to figure out whether one can realize many of these tasks on a network. And basically, what we found was that there were two regimes. So in one regime, you've got fairly weak synapses. Here you need 16 nodes to fire to cause a single neuron to fire. But then the number of actions this brain could do was a few thousand. Okay, so the actions were sequences of these tasks, of associations, assignment of memories, etc., etc. And if you remember, we're aiming for hundreds of thousands. So it turns out in a different regime, if you've got very strong synapses, so this is almost like a computer. So K equals 1 means a single neuron can cause its neighbor to fire. Then you can go into territory you're interested in. For realistic numbers, you can get hundreds of thousands of actions supported. So this brain can memorize lots of things in sequence. And even after it's memorized 250,000, it's fairly reliable on the tasks it started with a long time ago. Okay. Okay, so so some of these numbers, like the n's and the d's, etc., are known for simple neural systems, such as the locust, and one can make sense of those numbers. But what I want to finish on is the hope that one can actually test whether this kind of theory is right for the brain. So for the association task, so what's aggressive about the model is that the model assumes that if I have any two sets of neurons and run some protocol of exciting them, then I can have the effect of changing what the circuit will do. Okay, so the definition of this association task was that if I fire this set, then the result will be to cause this set to fire, to be reminded that the Omicron, if this means Omicron variant, B means dangerous, by some training, whenever I think of Omicron variant, I will know it's dangerous. Okay, so the theory assumes that for random sets of neurons, after certain training, the brain is clever enough to figure out how to change the circuit. So there's a strong assumption. But fortunately, this is exactly the kind of assumption which in principle you can test experimentally, because you can poke electrodes or using optical techniques, probe random sets of neurons. So random sets of neurons are the easiest ones to probe. And if your assumption is very strong that this should work for random sets of neurons, then in principle, these are ideal for testing whether the brain supports this. And the experiment's ongoing, trying to figure this out. Okay, so so we're still trying to find explanations of why the brain does these very everyday things, which we all take for granted, but we can't explain. Okay, well, thank you.
Thank you, Professor Valiant, for a wonderful lecture. We have some questions from the audience, which I'll read off for you. The first one is asking, they've heard that deep learning can currently train around 100 hidden layers in a model within seconds. And they were interested in your thoughts on when you believe we'll soon be able to mimic the actual brain in cases of NLP or image recognition, for example.
Well, thank you for inviting me here for start. So I think the question presupposes that the brain works like deep learning, which I think is controversial and unresolved. So my bet is that the brain works rather differently from deep learning, although and in fact functionally is good at different things. So one very basic issue people have raised is that clearly with backpropagation you need backward flow of information. You need two-way flow of information, which in the brain is hard to realize. Of course, people are trying to overcome that by having different kinds of algorithms. But so I would presume that deep learning is a very interesting engineering method, but it probably doesn't have that much to do with the brain.
Thank you. Next question. Can we make assumptions about non-neuronal components of the brain, such as glia and vasculature, using computer science?
Well, possibly in the long term. So what's attractive about looking at neurons first is that as I think I mentioned in the talk, is that the long distance communication is very stylized. So axons are all very similar and the transmission is all very similar. So there's one thing which is simple in the brain, is this long distance transmission of information by neurons. And this simplicity can be used as a constraint on the brain with which we can ask information. So I think everything else about the brain is just much more difficult. So I think those questions I haven't looked at, but I think we have to resolve what neurons are doing first, I think.
Thanks very much. The next question is why humans have a tendency to always remember bad memories or negative memories, incidents that happened a long time ago, but tend to forget happier moments easily. What are some of the underlying mechanisms? Your thoughts on that?
Okay, so that's not something I study, and I'm slightly surprised by the question. Is that true for everybody? I don't know. Are there studies of this? I'm not familiar with literature on this. I mean, people also talk about people suppressing negative memories. So I suspect it's a complicated phenomena, but I'm just not familiar with research in this area.
I'd imagine it's a very individualized process indeed. Yes. So, next question. May we learn your opinion regarding emerging computational methods, such as physics-informed machine learning that is used to enhance drawbacks of conventional neural networks?
So repeat, what's the new technology?
Regarding your opinions regarding emerging computational methods, such as physics-informed machine learning to
Oh,
enhance the drawbacks of conventional neural networks.
so these are different. I'm not exactly sure what the question means, but physics informed neural nets. So I'm not quite sure is the question about just different algorithms which you run on a conventional computer. So also I'm not quite sure whether is the goal to. I'm also not quite sure what drawbacks of neural nets one wants to overcome. So certainly trying to, if you have more information about the problem you're trying to solve, so neural nets are a very generic method of solving things. If you have more information, something called bias in machine learning, you may try to exploit that, but the successes in that direction are, I think, limited. So as far as I know, the powerful vanilla methods of machine learning, which are well programmed, are hard to compete with. But certainly there are millions of drawbacks, and everyone should try to overcome that. I'm not discouraging anything. I'm just always impressed by the most generic vanilla way of doing things in machine learning. Seems to do very well.
Thank you. So there are thoughts that no one ever really reaches their brain's full capacity. And can this be applied to cognition? So, for example, if this is true, why do we seem to reach cognitive limits? An example would be multitasking.
Well, yes, I think. Well, they're two different things. So with multitasking, you're reaching limits of your working memory. So your working memory is a very special part of your brain, which is to do with your attention, what you're attending to, and that brings together information from all over your brain. It's a very complicated piece of machinery, presumably. So that's got strict limits. But I think the limits there are very different from what you use your kind of main cortex for. That, use your main cortex for remembering your experiences over decades and decades and decades. And ultimately, there must be limits to that. But so the idea that we're underutilizing our memory and we could always have memorized more, I mean, I tend to agree with. But certainly with the models I have, there is the tendency that it does tend to fill up the brain, but a lifetime seems to be short enough to not to fill it up completely, I think. So I think the answer to the question is that our short-term working memory has got very strict limits, and that's multitasking. But our long-term abilities to store information is a very different thing, and we have a very impressive capability for that.
Thank you. Another question. So, when thinking about cognitive function, when you look at different different patients or different people, as you mentioned, variability in the number of neurons, the number of connections, and synaptic strength. So it would seem that there is variability from person to person in how these factors drive their cognitive outcomes. And these processes alone may very well be dynamic over time for the same person. Can computer science play a key role in helping to understand the individualized nature of these parameters and maybe even optimize them over time?
Well, that's certainly the kind of effort I'm involved in. But relating it to reality is difficult because, I mean, these basic numbers, you would have thought that we understood what they were on the average for humans and what they were for chimpanzees and other mammals, but it's very hard to get hold of these numbers. So apparently, experimental neuroscientists measuring these numbers doesn't bring them a great career prospect, so it's not a very fashionable thing to do. Whereas for people like me, these numbers are important. So it's a great question. I don't know the answer. So it could be that not differences in these numbers account for all kinds of mental capabilities or mental problems, but trying to understand the role of these numbers is exactly what I'm trying to do. But we haven't got the stage of saying anything about individuals yet.
To close, actually, a follow-up question. So when we think about computer science and neuroscience, two fields with certainly very different skill sets involved, and in our audience, we have our future innovators, our future scientific and engineering leaders in our community. What advice do you have for them in terms of in the future when they build their collaborations? Any advice on how to build strong collaborations, especially when they need other expertise to help answer the questions that they have? Any guidances on how to build stronger bridges in multidisciplinary research?
Well, yeah, I mean, it's a fantastic question. I've ventured in various directions to do this kind of thing. So one hears of this ideal story of people of different specialities sitting around the table and doing something together. But I found that to do anything, you have to understand the multiple fields in a single brain. that it's very hard to talk to people if there isn't some mutual understanding of the ground rules. So, for example, just one comment. So in computer science, there's a long tradition of working top down, bottom up, appreciating the many different levels of a system. Whereas neuroscience tends to be very bottom up science, that they look at they work up and they don't want to speculate on what they haven't demonstrated. So this is a very basic difference in outlook, which is difficult to bridge. One will find these very basic differences in philosophy, which I haven't found a simple recipe for overcoming.
Thank you so much for sharing your wonderful lecture with us today and for answering our participants' questions. Thanks again for joining the conference as well. Thanks, Professor Valiant.
Well, thank you. Thank you for inviting me. Bye.